Okay, so let's look at some numerical methods for constraint systems. Okay, so methods for constraint integration. Tend to fall into two general classes. Okay, so the first of which are methods based on integrating a related unconstrained ODE. Okay, and then the second one are basically methods based on a direct discretization of the constraint equations. Okay. All right. So let me just look at one very important set of examples. It's like of the direct methods. Okay. So direct discretization. And this has to do with what are called the shake and rattle methods. Okay. So shake and rattle are generalizations, if you will, of the Störmer-Verlet method. To constraint systems. Okay. And they're equivalent to each other in some sense, and they're also symplectic. Okay, so what I'm going to do basically is to start with the Störmer-Verlet method and then look at how you can modify it to deal with the constraints. Okay, so starting with Störmer-Verlet. Okay, you have mv at the half step is equal to mv at the original step minus h over 2, the gradient of the potential at the initial time. All right, so this is, if you will, a half step. It's like of the, it's essentially like a half Euler step, if you will. Okay, so then qn plus 1 is equal to qn plus h times v at n plus half, and then mv at the full step is equal to mv at the half step minus h over 2 gradient of the potential at the at the new step. Okay, so I should say that here it's like I'm using the notation where the superscript, it's like denotes, if you will, it's like the time at which the data is given. Okay, so if you prefer, it's like you can skip. It's what's oftentimes common is to skip the integer values, it's like of the velocities, and then just write it in half integer velocities. Okay, so if you do that, what you get is qn plus 1 is equal to qn plus hvn plus half, right? And then mvn plus half is equal to mvn minus half minus h, the gradient of the potential at qn. Okay. And if you prefer, it's like you can even eliminate the velocity variables altogether, and then you get what is oftentimes referred to as the leapfrog method. Okay. So eliminating the velocity variables. Lead to the leapfrog method. Okay, so m qn plus 1 minus 2 qn plus qn minus 1 over h squared. So this is, of course, just a finite difference approximation of the acceleration, right? The central approximation minus, right? So this is oftentimes referred to as the leapfrog method. Okay, so the constraint equations. Can be written in second order form. Right, m q double dot is equal to minus the gradient of the potential minus gq transpose times lambda, and then g of q equals to 0. All right, so you can apply the leapfrog method to this, right? Applying leapfrog yields the following. So m qn plus 1 minus 2 qn plus qn minus 1 over h squared is equal to the gradient of the potential minus g qn transpose lambda n. Again, it's like the superscripts here now denote the time step as opposed to an exponent, okay? And then g at qn plus 1 is equal to 0. Okay, so this is called shake discretization. This is called shake. And then, of course, if you wish, it's like you could reintroduce the position velocity form. Okay, so it can be recast into position velocity form. By setting the following. So Vn half is equal to Qn plus 1 minus Qn divided by h. And then Vn is the midpoint, is the average, it's like of the two velocities, right, at the half integer steps. Okay, and if you do that, it's like then what you get is that qn plus 1 is equal to qn plus hv at n plus half, right? mv n half is equal to mvn minus half minus h then 0 is equal to g at qn plus 1, and then vn is just 1 half vn plus half plus vn minus half. All right, so this is another form, if you will, the shake method. So I should say, well, so you might ask then what's the rattle method? So the thing to observe, it's like, if you will, it's like with the shake algorithm, is that the velocities don't necessarily satisfy the condition for being in the tangent space to the constraint manifold, right? So, and as you might expect, in order to guarantee that the velocities themselves, it's like, are on the tangent space, it's like a constraint manifold, the way you would normally do this is you add additional Lagrange multiplier-like terms, it's like, which then allow you to enforce, it's like, the orthogonality constraint between the velocity variable and the gradient of the potential, right? So anyway, so as it's currently stated, it's like the shake algorithm, it's like can be viewed, it's like as an algorithm, it's like on in position and velocity variables, which is what you see here, but with the property that the velocity variables don't necessarily live on the tangent space to the configuration manifold M. All right. And if you wanted to add additional multiplier terms, which then give you the freedom to guarantee that the velocities are in the tangent space to the configuration manifold, then you end up getting what is called the rattle method. Okay, but for now, this is the shake method, and then in a little bit we'll see what happens when you do rattle. Okay, so let me stop here.